Hello. Am I audible? Am I audible? Uh, so let me start the class. So, myself Kalpita Nath, and I am the TA of the course of Transport Phenomena. That is undergoing under Instructor Professor Sunando Dasgupta of IT Kharagpur. So, this is the week 5, that is the fifth problem solving class of Transport Phenomena. So, without further ado, I'll start the class. Okay, so we'll go on with the problem solving. So today's class is based on turbulent flows. So all the questions will be based on turbulent flows, how to calculate drag, or how to do other problem solvings. Like we'll see as we'll proceed further. So this is based on boundary layers on turbulent flows. Okay, so let us start. This is the first question that tells us about whether the statement is true or false. We have to identify. The turbulent viscosity, often known as eddy viscosity, is a strong function of position and intensity of turbulence. Unlike the dynamic viscosity, the eddy viscosity is a property of the flow, and hence it may even have a negative value in some regions of the flow domain. So tell us whether, tell me whether it is true or false. I'll give you 1 minute for this to think about it. Okay, so okay, the turbulent viscosity is often known as eddy viscosity, is a strong function of position and intensity. That is obviously true. And unlike the dynamic viscosity, the eddy viscosity is a property of the flow. Hence, it may even have a negative value in some region of the flow domain. Yes, eddy viscosity may have negative value, and even it depends upon the roughness of the pipe and everything. So yes, this is true. True statement. Both of them are true statements. So the answer will be A, that is true. Okay. Let us proceed to the second question. The Blachier solution for boundary layer equation is often quite restrictive in application since it is applicable only to the case of laminar layer over a flat plate. Laminar boundary layer over a flat plate. On the other hand, the solution for the general expression given by von Karman in the momentum integral method requires a knowledge of velocity. Requires a knowledge of velocity as a function of distance from the surface, and the accuracy of the final result will depend on how closely the assumed velocity profile approaches the real one. Yeah. So the Blazius solution for boundary layer flow is often quite restrictive to the application, since it is applicable only for the case of laminar boundary layer or a flat plate. Okay, now read out both of this statement and then identify whether one of them is true or both of them is true. If both of them is true, then mark it as true, otherwise mark it as false. I'll give you 1 minute for this. Okay. So the Blazier solution for boundary layer flow is often quite restrictive in the applications. Is applicable for laminar boundary layer. Obviously, it is applicable for laminar boundary as we have already studied about it in the previous class. The Blazier solution, right? And on the other hand, the solution for general expression derived by von Karman in the momentum integral method requires a knowledge of velocity as a function of distance from the surface. And the accuracy of findings will depend on how closely the assumed velocity profile approaches the real one. Correct. This is true. So both of the statements are true. In a turbulent flow, the fluid and the flow variables do not vary with time. For example, the instantaneous velocity vector will not differ from the average velocity vector in either magnitude or direction. In a turbulent flow, while the velocity might appear to be steady in its mean value, small random fluctuation in the velocity might occur about the mean value. Therefore, one could express the fluid and flow variables in terms of mean value and fluctuating value. I'll give 1 minute for this so that you can tell me whether it is true or false. What do you think about it? Okay. Okay. In turbulent flow, the velocity or the flow variables, the flow variables will vary with time. And for example, the instantaneous velocity vector will differ from the average velocity vector in both magnitude and direction. Okay, so yeah, in not either, in both magnitude and direction it will vary. So the first statement is false. So that's why the entire answer will be false. Let us proceed to the next question. In turbulent contribution to shear stress is called Reynolds stress. In turbulent flows, the magnitude of Reynolds stress is compared to the molecular contribution to stress. Uh, in turbulent contribution to shear stress is called Reynolds stress. In turbulent flows, the magnitude of Reynolds stress is comparable to the molecular contribution to stress in the entire flow field. So answer me whether it is true or false. in shear stress in turbulent is called Reynolds stress. And in turbulent flows, the magnitude of the Reynolds stress, whether it is comparable to the molecular contribution to stress or not. Just I'll give you 1 minute for this so that you can answer. And then we'll go on with the solution. So you take 1 minute for this question. I'm coming in 1 second. Okay. So this statement is obviously false. Why? In turbulent flows, it is found that the magnitude of the Reynolds stress is quite larger as compared to that of the molecular contributions. Except near the walls. Near the wall, there is viscous sublayer. There is viscous sublayer, we already know. And due to the no slip condition, as the wall is static, the flow there will be a bit slower. And the first layer will be static, that is in contact with the wall, and then it will be slower, and then gradually the velocity will increase as the turbulent flow comes in the picture. So the layer very close to the wall, that will be a flow velocity, and that is called viscous sublayer. And over there the molecular contribution is comparable, but rather than that, we can't say this statement is true. So that's why this statement is false. Okay, let's proceed to the next question. Consider the flow of liquid over a flat plate of length 1 meter and the velocity of the liquid is 50 meter per second. The kinematic viscosity of liquid is this, and using the boundary layer analysis, determine the value of mean skin friction at the length of x equal to 1 meter. For laminar flow it is given, for turbulent flow it is given. Now you have to find the Reynolds number and check whether in which flow regime it is. And then you have to find out the value of mean skin friction. Okay. So I'll give you 5 minutes to solve this question. After that, we'll go on to the solution. We'll proceed with the solution. Okay. Okay, so am I audible? I hope I am audible. So we'll go on with the solution of this question now. I'll share the writing pad. Okay. So question number 5. This is assignment. This is class. So, according to the question, first we need to calculate the Reynolds number, obviously, that is V rho x by mu, that is Vx by nu, that is V is 50 meter per second, 1 meter. Nu is 5.5 into 10 to the power 6 minus 6 meters per second. This is 9.09 10 to the power 6. That is greater than 5 into 10 to the power 5. This is the critical Reynolds number. So as it is greater than this, the flow is turbulent. Now we use momentum integral expression for the determination of the skin friction. CFL is equal to 0.0575 Reynolds number minus 1/5, as it is only given for turbulent flow. That is 0.0575 into 9.09 10 to the power 6 minus 1/5. That is equal to 2.3332 10 to the power minus 3. This is answer. So answer is C. Next. Choose the correct condition which is best described by the following boundary condition for momentum integral equation over flat plate. Eta is 1, Vx is equal to u is equal to 1, where u is phase stream velocity and all other symbols have their usual meaning. Okay, I'll give you 1 minute to answer this question, then we'll go on with the solution. This is nothing, just one word solution, so you should not take more than 10 minutes for this. Okay, let us wait for 1 minute then. Okay, so I hope you have understood what the answer will be. Let us go on with the solution. So this is question number 6. I hope the writing pad is visible. So eta is equal to y by delta, that we know obviously. So this is equal to 1 and Vx by u is equal to 1. This means y is equal to delta. Y is equal to delta, that is the end of boundary layer. So at end of boundary delta, Vx is equal to u. Okay. So at the edge of the boundary layer, the velocity approaching the free stream velocity, that is the answer will be B. Okay. Now question number 7. Determine the wall shear stress for the flow of flat plate using momentum integral equation if the velocity profile is u by u is equal to sine pi by 2 y by delta, where u is the free stream velocity. These are the expression for the wall shear stress. Now you undergo the solution and I'll give you 5 minutes for this. Then we'll go on with the solution. We have a lot of question today, so make it fast so that we can proceed with the solution faster. we'll undergo with the solution of question number 7. So, it is said to determine the wall shear stress over a flat plate using momentum integral equation, and the velocity profile is given. So, let us start. So, the velocity profile is given as sine pi by 2 y by delta sine pi by 2 eta from momentum integral equation, that is in lecture 23. Tau w by rho is equal to u square d dx of theta. Okay, so this we have learnt as shear stress that we need to find out. So tau w is equal to rho u square d dx of 0 to 1 small u d dx of theta. D dx of theta. Theta is this portion. U by u 1 minus u by u. Okay. Then delta d eta. Cos eta is equal to y by delta. So this was y. So this is, let me show you. This is d eta. Eta is equal to y by delta. It was dy, right? So we have given d here and delta here and delta here. So delta d eta. Okay. And as u is there, so that's why here u square. Okay. So this will be rho u square d delta by dx. 0 to 1 sine pi by 2 eta. This is eta, right? Sine pi by 2 eta. 1 minus sine pi by 2 eta d eta. So this will be rho u square d delta dx. This will be minus cos pi by 2 eta by pi by 2 0 to 1 minus 1 by 2 eta minus sine pi eta by pi 0 to 1. Okay. So this is equal to rho u square d delta by dx minus 0 plus 2 by pi minus 1 by pi plus 0. This 0 plus 0 and this is minus 0 is equal to rho u square d delta by dx 2 by pi minus 1 by 2. Tau w is equal to 0.137 rho u square d delta by dx. This is 0.137. This is tau w. So which one is this? This is C. Okay. So this is the solution of question number 7. If any one of you have any doubt, kindly tell me. And if not, let us proceed to question number 8. Assuming the fluid in question number 7 to be Newtonian, determine the value of delta by x. Choose the closest option. I'll give you 2 minutes to solve this, then we'll go on with the solution. let us get on with the solution. So this is the extension of question number 7, and it is said, if we assume Newtonian, then determine the value of delta by x. So if Newtonian fluid, then tau w is equal to mu del u del y, y is equal to 0. That is mu u by delta del small u by capital U, like we are just making it small u by capital U, and this will be del y by delta. So delta here, and u. So this is y by delta is equal to 0. This is mu u by delta d small u by capital U upon del eta. D small u upon d eta. Okay, sorry. Okay, so this is eta is equal to 0. That is mu capital U by delta d of sine pi by 2 eta d eta. This is eta equal to 0. So this is mu u by delta pi by 2 cos pi by 2 eta is equal to 0. Mu u by delta pi by 2 cos eta is 0, that is cos 0, that is 1. So this is equal to 1.57 mu u by delta. This is tau w if the fluid is Newtonian. Now, what is this delta by x? We need to find out. So tau w from question number 7 we found out to be, this is equal to 0.137. That is from momentum integral equation. So this will be same on this. Both of them is type tau w. Rho u square. This is u only, capital U. This just we have taken u here, no? U here. That's why both u. That's why u square. U square d delta dx, or 0.137 rho u square d delta dx is equal to 1.57 mu u by delta, or okay, delta d delta by dx is equal to 11.459 mu by rho u. Now we need to integrate delta d delta is equal to 11.459 mu by rho u dx, or delta square by 2, 11.459 mu by rho u x plus c. Okay, so the boundary conditions is x equal to 0, delta is equal to 0, obviously. At x equal to 0, there is no development of boundary. So 0 is equal to 0 plus c, so c is equal to 0. Therefore delta square by 2, 11.459 x mu by rho. Okay, so delta is equal to root over 11.459 mu x 2 by rho u. Therefore delta by x is equal to 22.92 mu x by rho u x square. So delta by x is equal to 22.92 mu by rho ux. Delta by x is equal to 4.8 rho ux by mu. 4.8 by root over Reynolds number, that is equal to 5 by root over Reynolds number. Therefore, delta by x is equal to 5 by root over Reynolds number. So, this answer will be A. Now, let us proceed to question number 9. Choose the correct statement. A momentum integral equation is a partial differential equation. Momentum integral equation cannot be used for non-momentum fluid. Momentum integral equation can be used for both laminar and turbulent flow. And all the above statements are true. Which one is true? I'll give 1 minute for this and then we'll go on with the solution. And then we will see which of the option will be correct. Okay. So this is rather a simple question. So momentum integral equation is a partial differential equation. Obviously, momentum integral equation is a partial differential equation. We are just integrating it. So the option A will be the correct answer. Let us proceed to the next question. The thickness of the boundary layer delta is arbitrarily taken as distance away from the surface where the velocity reaches 90% of the free stream velocity. For the flow of fluids at very low speed and with large viscosity, it is possible to delete the inertial terms from the Navier-Stokes equation. However, for flows at high velocity and small viscosity, It is not always logical to delete the viscous terms from the Navier-Stokes equation. Okay. For cases with low fluid velocity, all the individual terms on the left hand side of the Navier-Stokes equation, let us write the Navier-Stokes equation first. Minus del, this is 10, minus del P plus rho G plus mu del square V vector is equal to rho dV vector dt. This we can write as V vector del V vector. The right hand side, with low fluid velocity, all the individual terms on the left hand side of the Navier-Stokes equation are small relative to each other. On the contrary, for the case with low velocity and for the low viscosity and high velocity, with low viscosity and high velocity, the product of velocity and its gradient, that is this one, cannot be considered small relative to the other terms. This cannot be considered small. That's why it is not always logical to discuss the viscous term, discard the viscous term for such situations. So the option is A, true. Now this is a problem that we need to solve. Okay. So during the flow over a flat plate, the laminar boundary layer undergoes a transition from laminar to turbulent. Goes a transition to turbulent boundary layer from laminar as the flow proceeds in the downstream. It is observed that a parabolic laminar profile is finally changed to a 1/7 of the power law velocity profile in a turbulent regime. For find out the ratio of the turbulent to laminar boundary layers if the momentum flux within the boundary layer remains constant. Okay. So, do anyone have any doubt on understanding the question? If not, then you can proceed with the solution, and we'll I'll give you 5 minutes for this. Then we'll go on with the solution itself. So let us start with the solution now. This is question number 11, right? First is assume width of the boundary layer be A. Then momentum flux A is equal to rho u A dy u. This is velocity. This is mass. So both of these gives momentum flux. This is momentum. Okay. So this is rho u infinity square A delta small u by capital U infinity whole square dy by delta. Rho u infinity square A delta U by capital U infinity whole square delta. It is equal to y by delta. Now, where eta here is equal to y by delta. For laminar flow, parabolic velocity profile is maintained. It is already said. Therefore, small u by capital U infinity is equal to 2 eta minus eta square. How did this came? Let me show you. 1 second. Okay, I'll show you this derivation later on, and you can you have already, I think you have already studied this. I'll show you this. There is another question where this will be applicable. Over there, I'll show you how to use. Okay. So for laminar flow, the momentum flux is rho u infinity square A delta laminar 0 to 1. So let me shift it to the next line. This will be there, and then 0 to 1 4 eta square minus 4 eta cube plus eta to the power 4 delta. This we have just squared it. Rho u infinity square A delta laminar 4 by 3 eta cube minus 4 by 4 eta square plus eta to the power 5 by 5. This is 0 to 1. This is rho u infinity square A delta laminar 4 by 3 minus 1 plus 1 by 5. Rho u infinity square A delta laminar delta laminar 8 by 15. Now, for turbulent flow, the velocity profile follows 1/7 power law. Now for turbulent flow, u bar by u infinity is equal to e to the power 1/7. So A turbulent is equal to rho u infinity square A delta turbulent. This is 0 to 1 eta to the power 1 by 7 to the power square d. So is equal to rho u infinity square A delta turbulent 0 to 1 eta to the power 2 by 7 d eta. This is rho u infinity square A delta turbulent eta to the power 2 by 7 plus 1 by 2 by 7 plus 1, 0 to 1. Rho u infinity square A turbulent delta turbulent. Okay, just 1 second. A delta turbulent 7 by 9 eta to the power 9 by 7, 0 to 1. 7 by 9 rho u infinity square A delta turbulent. Comparing the momentum fluxes. A laminar is equal to A turbulent. Okay, so it is said the momentum flux, the boundaryless of the momentum flux, if the momentum flux with the boundary remains constant. So the momentum flux for laminar and turbulent will be equal. So u infinity square A delta laminar 8 upon 15 is equal to 7 by 9 rho u infinity square A delta turbulent. So this will give delta laminar upon delta turbulent is equal to 7 by 9 rho u infinity square A by 8 by 15 rho u infinity square A. So this will give 7 by 3 into 5 by 8 is equal to 35 by 24. So therefore delta laminar upon delta turbulent is equal to 35 by 24. This is the solution. Okay. So next question is, air is flowing over a flat plate and the free stream speed is 15 meters per second. At a distance of 1 meter from the leading edge, calculate delta and tau w for completely laminar flow and completely turbulent flow with a 1/4 power velocity law. Power law velocity profile. For turbulent, fully developed flow in pipe, F is given, where Reynolds number is also given, and for eta is equal to 7 also. U average upon U becomes equal to 0.8. This is 1/7, not 1/4. Okay. Okay. So let us proceed with the solution. Okay. I'll give 5 minutes before proceeding, and after that we'll proceed with the solution. Try to solve it. Okay. We'll carry forward with the solution of question number 12 now. So there are two parts. First one is part A, which is for completely laminar flow. So if it is completely laminar flow, this we have already taken on earlier. So delta by x is equal to 5.48 upon root over Reynolds number. This we already know. And tau w is equal to mu del u by del y is equal to 0. Now Reynolds number is ux by nu, that is 15 into 1 by 1.5 into 10 to the power minus 5, that is 1.0 into 10 to the power 6. So delta is equal to 5.48 by 1.0 into 10 to the power 6 into 1 meter. This is 5.48 millimeter. Now okay, how did this came? First we will get to know about this. For laminar flow, we assume a polynomial for velocity profile. That is u is equal to a plus by plus cy square. The boundary conditions are, first is y is equal to 0, u is equal to 0, and y is equal to delta, u is equal to a. That is at the edge of the boundary line. And this is at the 1. At y is equal to delta, again because of the liquid air interface, the shear stress will be 0. That is du dy is equal to 0. Therefore, u by u is equal to, if you put on this boundary condition, we'll get that to y by delta minus y by delta square. That is 2 eta minus eta square for laminar flow. Okay. Now let us continue from there. Now tau w is equal to mu del u del y at y is equal to 0. So this is mu u infinity. This is mu u infinity by delta. Del small u by capital U infinity by del y by delta. This is y0. Mu u infinity by delta del eta of small u by capital U infinity, eta is equal to 0. Mu u infinity by delta d eta of 2 eta minus eta square, eta is equal to 0. Tau w is equal to mu u infinity delta 2 minus 2 eta, eta is equal to 0. Mu u infinity by delta into 2 is equal to nu rho u infinity 2 by delta. 1.5 into 10 to the power minus 5, 1.23 into 15 into 2. 5.48 into 10 to the power minus 2, minus 3. So tau w becomes 0.101 meter per meter square for laminar flow. Next is for completely turbulent flow of 1/7 power velocity profile. So this is part B. For turbulent flow, small u by u infinity is equal to 1/7 power law, that is y by delta to the power 1/7. Now delta by x, for this we know that for turbulent flow it is Reynolds number 1 by 5. Previously we have already found it. 0.370 upon 1 into 10 to the power 6 1 by 5 into 1 meter. So this gives 23.34 mm, or delta by x is equal to 0.0233. Now momentum thickness for turbulent flow. Delta star is equal to 0 to delta u by u infinity 1 minus small u by capital U infinity dy is equal to 0 to delta y by delta 1 by 7 1 minus y by delta 1 by 7 dy. Okay, now this gives delta star to be 7 by 72 delta. Okay, now for turbulent flow, Darcy friction factor for fully developed flow is minus dp dx is equal to rho f u average square by 2d. This is equation 1. This is the fully developed flow velocity profile, and shear stress will be okay. So let us change another color. This side is tau w, this side is dp dx, and this side is again tau w. This is x direction. Now balancing forces for fully developed pipe flow dp dx pi r square is equal to tau w to pi r minus dp dx to tau w by r. Comparing equation 1 and 2. One is this one, rho f u average square by 2d. This is equal to 2 tau w upon r, or from here we get tau w to be f by 8 rho u average square. This is equation 3. Blasius found empirical formula for f as f is equal to 0.3164.35. These have already been provided in the question. Okay, so this is equation number 4. Now substituting four in equation 3. Tau w is equal to 0.3164
0.3164 by 8. Reynolds number 0.25 rho U average square. So this is 0.03955 mu to R U average 1 by 4 rho U average square. 0.03325 rho U average 7 by 4 by R 1 by 4 0.03325 rho U average U bar 7 by 4 U bar 7 by 4 nu by R 1 by 4. For 1/7 law y by delta 1 by 7. U average U bar is equal to 0.8. Therefore, tau W is equal to 0.3225 rho 0.87 by 4 U bar 7 by 4 nu by R nu by R 1 by 4. So tau W is 0.0225 rho U bar 7 by 4 nu by R 1 by 4. This is tau W. Now tau W by rho U bar square is equal to 0.0225 U bar minus 1 by 4 and nu by R to the power 1 by 4. This gives 0.0225 nu by U bar R to the power 1 by 4. Now substituting U infinity for U bar and delta for R. Tau W by rho U infinity square is equal to 0.0225 nu by U infinity R to the power 1 by 4. Therefore, tau W is equal to 0.0225 rho U infinity square nu U infinity R 1 by 4. Okay. Now, putting values. Tau W is equal to 0.0225 into 1.23 into 15 square nu by U infinity x x by delta 1 by 4. This is Reynolds number obviously. So this is 0.0225 into 1.23 into 10 into 15 square into 1 by 1 into 10 to the power 6 0.0233 per 1 by 4. This gives tau W to be 0.502 meter per meter square. And for laminar, what we got? Laminar tau W was beautiful laminar tau W. This one 0.101. So if we compare, we can see that turbulent boundary layer has large shear stress than laminar, because that was point 1 is 0.5 approximately. Laminar boundary layer. Okay, so we are done with question number 12. Now let us proceed to question number 13. So water flows at velocity
at free stream velocity of 1 meter per second. That is passing of flat plate with L is 1 meter in the flow direction. The boundary layer is stripped, so it became turbulent at the leading edge. Evaluate the disturbance thickness delta, displacement thickness delta star, and wall shear stress tau W at x equal to L. Compare with laminar flow maintained to the same position and assumed 1/7 power law turbulent velocity. I'll give you 2 minutes to solve this as we don't have much time. I don't think we'll be able to solve this today, but yeah, we'll solve one part of this at least. Okay, so let us proceed with the first part of solution. Apply results from momentum integral equation for turbulent flow. Governing equation is delta by x 0.382, Reynolds number 1/5. Then delta star is equal to 0 to infinity 1 minus small u by capital U dy, and CF is equal to tau w half rho u square, 0.0594 Reynolds number 1/5. Now it's given that x is equal to L with
nu is equal to 1.00 into 10 to the power 6 meters per second. For water at T is equal to 20 degrees Celsius. Therefore, Reynolds number is UL by nu, that is equal to 1 meter per second, 1 meter 10 to the power 6 meters 10 to the power 6. So 10 to the power 6, that is greater than 5 into 10 to the power 5. Therefore, the flow is turbulent. So first is delta L. Delta L is 0.382 by Reynolds number to the power 1 by 5. Okay. It's 0.382 by 10 to the power 6 to the power 1 by 5 to 1 meter. That is 0.0241 meter. So delta L is equal to 24.1 millimeter. Okay. For turbulent flow, at least let us find out, and the last part of this, there is a comparison with laminar flow that we will do next time. Okay. So now small u by capital U, now we need to find the displacement thickness. Right. Displacement thickness delta star is y by delta to the power 1 by 7, that is eta to the power 1 by 7. Therefore delta star is equal to 0 to infinity 1 minus small u by capital U dy. Delta L 0 to infinity 1 minus small u by capital U dy by delta. Delta L is 0 to delta 1 minus small u by capital U d of y by delta. That is eta is equal to y by delta when y is equal to 0, eta is equal to 0. Y is equal to delta, eta is equal to 1. Right. Therefore, delta L star is equal to delta L 0 to 1 minus small u by capital U d eta. Delta L is 0 to 1 minus eta to the power 1 by 7 d eta. As small u by capital U is equal to eta to the power 1 by 7, delta star is equal to delta L eta to the power 1 by 7 plus 1 by 7 plus 1. This is 0 to 1. Delta L eta minus eta to the power 8 by 7 by 8 by 7. This is 0 to 1. Delta L 1 minus 7 by 8 is equal to delta L by 8. Therefore, delta L star is equal to 24.1 by 8 mm. That is 3.0125 mm. This is delta L star. Now, the skin friction is equal to 0.0594. For turbulent flow, it is this into Reynolds number to the power 1 by 5. 0.0594 by 10 to the power 6 whole to the power 1 by 5. This is 0.00375. So therefore, shear stress we need to find out. This is half CF into half rho U square. So this is 0.00375 into 1 by 2 into 999 kg per meter cube into 1 square meter square second square Newton second square kg meter. Tau W is equal to 1.87 Newton per meter square. This is the shear stress. Now we need to find out for laminar flow everything for laminar flow too. And after that, we need to, for laminar flow, it will be a bit lengthier. And after that, we need to find the ratio of the disturbance thickness, or the displacement thickness, and the wall shear stress. Okay, we'll do it next day. Okay. Okay. Thank you for joining the class today.
today the class will be up till here, and
Let me stop the screen sharing.
I'll meet you all next week. Okay, thank you.